Amen. Thank you. All right, how about comments from General Conference? Any memorable talks or quotes or themes? Christine? Yeah. Yeah, it's such a powerful talk. I mean, I was thinking this morning, like from things from that talk, that exact thing, like what can I do? What would I do if I had more faith? And then commit to do those things. Very nice. Others? Rochelle? Oh, is it Elder Stevenson? Yeah. Yeah, yeah. I had never heard that before, the story about the rabbit experiment. It was so, so cool. But I had heard from an author of another book, he said, the more affluent that our society has become, the more depression there's been, the greater number of suicides, the greater number of broken marriages. I was like, he just started listing off all these problems. You're like, and you're like, why would all those things increase with more affluence? The thing is, it draws your attention away and your focus away from those things that are most important, which are those things of the heart and relationships. So yeah, really, really interesting. Okay, one more comment? Yes. Yeah. Yeah, it was so cool. Sunday morning, President Nilsson was the only one that was originally from America, like, you know, that was native to America that spoke. It was just everyone else was foreign. So, so cool. Definitely, yeah, definitely international. Okay. So just a quick note. So 7.4 is a really big section. It's the last section that we cover. We're going to spend 2 days on it, but you need to read enough and watch the videos so you can do the WebAssign, because the WebAssign is due next time, okay? So what you need to know for the WebAssign is basically how to do by hand a singular value decomposition. It's similar in a lot of ways to the orthogonal diagonalization that we are covering today. And the 5.4 homework, I took off one of the proof problems on the 5.4 homework. You have a whole week to do homework, the written homework for 7.4, and I have included a couple readings from the book that I've had you read in the past that does some applications of singular value decomposition, as well as some other eigenvalue decompositions. So you just have to read it and write a short paragraph. So. And student ratings are up. You can start rating the class, so you can go there. I really appreciate the feedback. I read through every single comment that anyone writes, and I use it to help improve the class for next time. So please do that. Okay, so go ahead and work on these problems. Oh, actually, it's like first, I wanted to talk about a couple things on these problems. So I give you the eigenvalues, but this is a situation where this particular matrix, you actually don't need to do any computation to find out what the eigenvalues are. Because you're trying to figure out what can you subtract off the diagonal and make it a non-invertible matrix, right? So clearly 5 has to be 1, because if you subtract off 5, you're going to have a column or a row of zeros, okay? But then, because this is symmetric down here, with this 2 by 2, okay, this 1, 3, 3, 1, I can make this non-diagonalizable if I can get both of these 3s, if I can turn them to 3, or if I can turn them to a -3. So because it's symmetric, I have something more to work with. And so I can think, hey, how can I change these to 3? Well, if I subtract off a -2, if I add 2 to both of those, I'll have 2 columns here that are that are linearly dependent. So a -2 has to be an eigenvalue. And if I make this one a -3 and this one a -3, then this column will be a -1 times that column. So what do I have to subtract off? 4. If I subtract off 4. So you actually don't have to do any computation there. If you just think about what can I subtract off to get linearly dependent columns, then you can get all of those. Okay, and you had a quick question? Oh, are they up on Learning Suite? Yeah, do you want to see if you can, we'll get Michelle on that right now. Okay, thanks. Okay, go ahead. Grading, we're currently grading the exams. I don't know when we'll have them. Hopefully by the end of the week, I imagine. Thanks for asking, sorry.
Okay, so
It showed up on the board here what it means to be orthogonally diagonalizable. Okay, we're looking for an orthogonal matrix Q so that A equals QD Q transpose. Okay, and these are based off of the Q is based off of the eigenvectors of A. So you can start by looking for those. All right, let's start talking through this. So the place we start with orthogonal diagonalization is the same place we start with regular diagonalization. We're going to search, we're going to find our eigenvalues, and then use each of those to find the eigenvectors associated with those eigenvalues. Okay. So here we subtracted 5 off the diagonal. There's a column of zeros. Sorry, there's a column of zeros and a row of zeros, but with the row of zeros, we're going to move to the bottom. And we don't run into a column of zeros very often, but if you have a column of zeros, that's a free variable. There's no pivot position there. So this tells us, hey, x, we're going to make x or x1 a free variable. So here you could rewrite this as x equals t, y equals 0, z equals 0, because you're really augmenting. Not all the students write down the 0 over here, but you're really augmenting this with 0, 0, 0. You want to find out the null space. You want to find out the solution of when can I multiply this matrix? What can I multiply this matrix by to get the 0 vector out? And in this case, this says, well, y is 0, z is 0, x is a free variable, so I can let it equal anything. So your solution, x, y, and z, for any vector is 1, 0, 0 times t. So we just care about this vector or some multiple of that vector. So we get the eigenvector, and red has the square root of 1 squared here equals 1. Why is he thinking that? Over here, he divided by something in these other ones. Why wasn't he just happy with 0, 1, 1 here and 0 and negative 1, 1? We want an orthogonal basis. Sorry, we want an orthogonal matrix, and that means we have to have orthonormal columns. So we have to divide by their length. So here he calculated the length, which is just 1. We don't have to change that one. Okay. Similar thing, subtract off. Subtract off 4, row reduce. Put it in terms of equations. X equals 0, y equals z, z equals itself. So you get the 0, 1, 1. And if you're not sure, like you're trying to find out if the vector that you can multiply this by to get 0 out, dot product, do the dot product with this vector in each of the rows. Is 0, 1, 1 dotted with 1, 0, 0, isn't that 0? Yeah. Is 0, 1, 1 dotted with 0, 1, negative 1, isn't that 0? Yeah, and those are all zeros, so yeah. So you can check to make sure these make sense. And the length of this, the norm is square root of 2, so you have to divide by the square root of 2. And do that again, similar results. You get 0 and negative 1, 1. Length of that is square root of 2, so you divide by the square root of 2. So you put those rows together, the columns together to make Q. And notice the order matters. Same thing when we did diagonalization. Since I put 5 here first, the eigenvalue associated with 5 goes here. And then since we put 4 here, the eigenvalue associated with 4 goes there. Since we put eigenvalue negative 2 there, the column associated with negative 2 goes there. Okay. All right, questions on this? Yes, Isaac? Isaiah, dang it. Okay. Yeah, that's right. There's no specific order that I have to put these, but so if I started with negative 2 over here, then this column, it would be at the beginning. In the next section with singular value decomposition, there is a convention that we always will go highest value to lowest value. And that's because in most of the contexts where you use singular value decomposition, the columns associated with the largest value are the most important, and those are the ones you end up using. So it's just easier to put to everyone's just expecting those most important columns over here. So, okay, great question. Other questions? Okay, so here we do, this is the second part. So it's how to do what is the spectral decomposition. So so I'm just going to write this out really fast. Okay, so if you have these Q vectors, and this Q1 is the first column, or the column, the orthogonal column associated with lambda 1, and lambda 2 is the orthogonal column you have in Q associated with lambda 2, etc. Then this is the orthogonal decomposition. This is another way to write our original matrix. And it's pretty slick, and the reason it's so slick is because it's so kind of slick and compact. This is just three products, three vector products, or not dot products, because a lot of the other dot products go to 0 because you're working with orthogonal columns and rows. So you get this cool decomposition, and so you do that multiplication. And before we finish this, I'm going to jump to a slide. Have you guys think about something for a second? Okay, so talk to your neighbor about what is the difference between those two products. All right. So heard a lot of people say, well, the first one is just a number, right? The first one is what we'd write at, we would call a dot product. We might write it a different way, but the first one, I take 1, 2, 3, multiply the 1 times the 4, 2 times the 5, 3 times the 6, add them together, I just get one value, right? What about this second one? Christine? The 3 by 3 matrix. How do you get the entries? Yeah, so we've got this, the 1 times 4, 1 times 5, 1 times 6, 2 times 4, 2 times 5, 2 times 6. You can think about it as 4 times this column. Is that the way you were thinking about it? Yeah, 4 times this column is your first column. 5 times this vector is the second column, and 6 times that vector is the third column. I have it written up here. So, except on this chord. Okay, yeah, so here it is. So 4, 8, 12, that's 4 times 1, 2, 3. 5, 10, 15, that's 5 times 1, 2, 3. 6, 12, 18, that's 6 times 1, 2, 3. Or you can think about it as 1 times 4, 5, 6, that's your first row. 2 times 4, 5, 6, which is 8, 10, 12, that's your second row. 3 times 4, 5, 6, which is 12, 15, 18, that's your third row. So my question is, why is this a rank 1 matrix? Or talk to your neighbors. All right. So group I talked to said, well, you have copies of the same row or copies of the same multiples of the same row or multiples of the same column. This 4, 8, 12, you can get to 5, 10, 15 by multiplying by the right thing, which is 5/4. And you get 4, 8, 12 to 6, 12, 18 by multiplying by the same thing, which is 3/2, whatever it is. Or this way, it's easier for me to see rows. 4, 5, 6 times 2 is 8, 10, 12 times 3 is 12, 15, 18. So if I start row reducing, I can eliminate this next row, the second row and the third row with just multiples of that first row. And so I'll just end up with 4, 5, 6 and everything, the other rows will be 0. So you can do that, always do that with this kind of product. So we're going to be dealing with these kind of matrices, these kind of rank 1 matrices next time also. Oops, I'm missing something. Oh yeah, so it's called the outer product. Sometimes the dot product is called the inner product, kind of collapses into just one number. The outer product kind of expands it. So you get the explosion and the implosion of the matrices. So the inner product is an implosion to a number. The outer product is an explosion into a larger matrix. So this is called the outer product. So you'll bump into that language when you read in the textbook, and you'll see it later in other classes. Okay, so here we have these outer products. So I can think about this as just 1 times that. 1, 0, 0 will be my first matrix. Then 0 times that. Sorry, not first matrix, first row. Then 0 times this will be my second row. 0 times this will be my third row. And I multiply all that by 5. So boom. And then the same thing over here. 0 times this row will be the first row. 1 over the square root of 2 times this row will be the second row. 1 over the square root of 2 times this row will be the third row, and then I multiply all that by 4. So before I multiplied by 4, it would just be 0, 0, 0, 0, a half, 0, a half. And then you multiply by 4, you get this one. And similar thing over there. Okay, and now we can check and make sure we got this right. So you can add up. If you add up those 3, then you better get our original matrix. You better get this one. So, okay. All right. Any questions on that? Okay. These are kind of the typical, straightforward computational problems you'll find on the final exam. Okay. So you should know how to make these, do these. Now, for the stuff students are not so, things that are not so straightforward. Okay. This is from most of this is from a past final. So this is one of those mark all that's true. So which of these must be true? So find all the true statements in there. So go ahead and work with your neighbor. See if you can figure those out. Why is that not hard? understand the quote, but why does that, I mean, you know, the saying go in a heart? It just doesn't seem like. I missed that, but yeah, it's nice. Any questions back here? Anything you're struggling with? Okay. Any questions? Okay. Any questions? Okay, take one more minute. All right. So, okay, let's shoot for the first one here. We're just going to do thumbs up is true, thumbs down is false. We'll see how you guys are feeling. Okay. Thumb sideways, you get them chopped off. No, I'm just kidding. Okay. All right. Okay. If you don't put up a thumb, then you should lose a hand or something. I'm just kidding. We don't do things like that anymore. A is worth, I mean, hopefully we didn't do. There are cultures where you would lose hands for doing things, right? We don't live in one of those. A is orthogonally diagonalizable. True or false? Okay, lots of thumbs up. Okay, so this is true. So the big theorem, one of the big theorems in this section is if you have a symmetric matrix, then it is orthogonally diagonalizable. And if you have a matrix that's orthogonally diagonalizable, it is symmetric. So that is like the big thing of the big theorem of this section. So that's the spectral value theorem. So if the theorem has a name in an undergraduate class, then it must be important. So that's, yeah, know that theorem. So if you know, if it's symmetric, then you get this really nice orthogonal diagonalization that comes with it that you know you can create. Okay, number B, there is an orthogonal basis for R4 consisting of eigenvectors of A. True or false? Okay, a few more false in this one. This is true. So because it's orthogonally diagonalizable, you create the Q matrix, and this Q matrix, it spans all of R4 or Rn. So and it is an orthonormal basis here. So that's also true. The geometric multiplicity of the eigenvalue 5 is equal to 2. So true or false? Some people not wanting to show their thumbs. Okay, so this is also true. So this is not true in general, right? If we didn't know that A was symmetric, then you should definitely vote false on that one. We don't know for sure. But because we know that A is orthogonally diagonalizable, then we have to get 2 eigenvectors out for 5. When we subtract off that 5 from the diagonal, not in this matrix, but whatever that 4x4 matrix is, when we subtract off 5 on down that diagonal and augment it with 0 and find the basis for that null space, we are going to get, we have to get out 2 vectors. If we don't, then we couldn't diagonalize. But symmetric matrices are always orthogonally diagonalizable. And so they're always diagonalizable. So we have to get out 2 vectors here. So we know that in this case that the geometric multiplicity has to equal the algebraic multiplicity. Okay, not true for general, but with the symmetric matrix, it is. A is not invertible. Thumbs up for true, thumbs down for false. Okay, up, down, nice job. I think all of them are down. Yeah, because none of the eigenvalues are 0. Right, that's how you'd know. If the eigenvalue was 0, then it's non-invertible. If it doesn't have an eigenvalue of 0, then you know it's invertible. So that's one of the equivalent statements to being an invertible matrix. Okay, the rank of A is 3. Thumbs up if you say true. Thumbs down if you say false. False, right? Because we have 4 non-zero eigenvalues. For every non-zero eigenvalue, and it's also invertible, so we know the rank has to be 4 because it's a 4x4 matrix. So rank can't be 3. A equals A transpose. True, because it's symmetric. That's the definition of a symmetric matrix. Okay, here's the hard one. I shouldn't have said that. No, that may have given you a clue about whether it's true or false, and you're going to be like, well, would he say that if it was true, or would he say that if it was false? Okay, any basis of the eigenspace associated with the eigenvalue 5 is an orthogonal basis. True or false? Okay, pretty good mix here. All right, so the answer here is false. Okay, now why is it false? So if we think of going through this process of subtracting 5 off the diagonal, and row reducing, we know we're going to end up with 2 eigenvectors, right? The null space of this will end up with 2 eigenvectors, and they're going to be linearly independent. So the eigenbasis will have 2, but they may not be orthogonal right now. They may not be orthogonal right now. The book did an example where there were 2 eigenvectors associated with an eigenvalue. They weren't orthogonal. What did the book have to do to get them orthogonal? Gram-Schmidt, right? You pick one, and then as your first vector, and then you do Gram-Schmidt orthogonalization on the other one to adjust it, because you have 2 vectors. They form a basis for the eigenspace, which would be a plane. And so what you do is you do Gram-Schmidt to rewrite one as an orthogonal vector, so they're orthogonal. So you might not get it right when you first go through the process, so then you have to do Gram-Schmidt. Okay? All right. Okay, any questions about these? Yes. Yeah, so it means that any vector in one eigenspace dotted with, so for those that are online, the question is, what does eigenspaces, if we say these eigenspaces are mutually orthogonal, what does that mean? So that means if you have a vector in one eigenspace and a vector in another eigenspace, you take the dot product, they'll always be 0. So because you can't really say it's not that all eigenvectors are orthogonal, because these were 2 eigenvectors we may have found, and they're not orthogonal. But if I take a vector anywhere in this space and I dot it with a vector in any of the other eigenspaces, then they will be orthogonal. So, okay, good question. Other questions? Okay, I'll give you another problem, and then let me just make sure. Oh, actually, let's do this. This is more fun than doing another old final exam problem. So this will help you see, hopefully. Okay, well, that didn't work. That's what that nice sound told us. Copy. There we go. All right. So here, I can go through lots of different vectors, kind of on this unit circle. And this matrix up here in the upper left, it does the transformation, multiplies that matrix times this vector, and then the new vector shows up there. So get some sort of stretching and squishing going on. The eigenvectors, here's the eigenvectors. So notice those eigenvectors are perpendicular, right? We can convince ourselves they're eigenvectors first. If I get on that red line, then the transformed one stays on the red or the yellow line. Okay, so they're eigenvectors. But look, they look orthogonal. But notice the matrix is symmetric. But if I change this to be non-symmetric, look, now those vectors are not orthogonal. Okay, if I change it to something different, look, now they're orthogonal again. So look, now they're orthogonal still because it's symmetric. But as soon as I get, oops, this is that's not happy because that's not an invertible matrix. But that's not much. That's not off by much. There. This is near almost invertible, not quite. And you can see the eigenvectors are pretty close to each other. So, but any symmetric matrix that we pick, I don't know why I didn't like my, well, there you go. So then they're orthogonal. Okay, so that's what that theorem, that spectral theorem says is, part of what that spectral theorem says is if I've got a symmetric matrix, you're going to have orthogonal eigenvectors, or if they come in sets, they have a higher geometric multiplicity than one, then you can actually you can create them so they're orthogonal, adapt them so they're orthogonal. Okay. Any questions? Okay. Have a great day. I'll give you 2 extra minutes.